All right, in our last video, we talked about about thermochemistry, about how we're looking at the changes in energy with a chemical reaction. Today we're going to focus on how we measure that energy. Since we're looking at how things are changing, we've got to know how to measure them. All right, just a quick review about heat and some definitions. Heat, when we talk about heat, we're talking about the energy that's being transferred from one object to another because there's a difference in temperature, because there's the difference in the kinetic energy, which again is what temperature is. It's the average kinetic energy of the particles. Because there's a difference in that kinetic energy, some of that energy is transferred from one object to another, and that's what we call heat. Now, there are three temperature scales that we can use: Celsius, Fahrenheit, and Kelvin. We're going to be mostly using Celsius moving forward. We definitely will not be using Fahrenheit. Kelvin is going to come back, so don't forget how to use that. And again, the symbol that we use, the abbreviation, the variable that we use for heat is lowercase q, because, you know, chemistry isn't hard enough. We've got to give you a variable that makes absolutely no sense. And when we measure energy, the first thing that we need to do is define some units. We've got to have units if we're going to measure something. So the metric system unit for energy is called the joule, spelled Joule, and the symbol is a capital J. Hey, at least this one makes sense. This unit of energy, the joule, was named after James Prescott Joule, who was an English physicist in the 19th century. And his study of energy led directly to our understanding of the law of conservation of energy. And so we named the metric unit of energy after him. Again, the joule, capital J. If only it were that easy, right? There are actually two other units of energy that we can use that are acceptable to use in the metric system. The joule is the official unit, but it's acceptable to use either one of these units that we're about to talk about. So I want you to be familiar with them. I'm mostly going to use the joule in class, but if you ever look anything up, you've got to be familiar with these other ones. So the first is a calorie. Now, you've probably heard calorie before. It does not mean what you think it means. A calorie, in chemistry language, a calorie comes from the Latin word calor, meaning heat. It's also the Spanish word for heat, calor. It's the amount of energy required to raise the temperature of 1 gram of water 1 degree Celsius. That is the definition of a calorie. It's a measurement of energy, and it's the amount of energy that 1 gram of water to raise that temperature by 1 degree Celsius. That is the definition of a calorie. Turns out that 1 calorie is 4.184 joules. You don't need to remember that. It's just, if you ever need to convert from one to the other, I'll make sure you get that information. Now, the calorie that you are probably familiar with is a capital C calorie. It's what we call the food calorie. It's actually a kilocalorie. It's 1,000 calories. So on the package of your food, when it lists the calories, that's actually, if you want to know the calories, those are actually kilocalories. So you have to multiply that by 1,000 to find out the actual amount of calories in your food. So if you have something that's, for example, 20 calories in it, well, it's actually 20,000 calories in it. It's a kilocalorie. So and the way we distinguish between those, again, because chemistry is not confusing enough, we give two different units the same name. Calorie with lowercase c is the amount of energy to raise 1 gram of water by 1 degree Celsius. Capital C calorie is the kilocalorie. Okay, so and I will make sure to be very clear which one we're talking about. Lowercase calorie and capital C calorie one is a kilocalorie, and that's the capital C, right? So one capital C calorie is 1,000 lowercase c calories. Because, why not? We're not confusing enough. All right, now that we've got our units, let's get into a little bit of practice of converting these units. So let's go ahead and start with a conversion from joules to kilojoules. All right, so converting from joules to kilojoules. Remember that this K here, the prefix kilo means 1,000. So there are 1,000 joules in every kilojoule, right? So we have 1,000 joules equals 1 kilojoule. So the example we're going to go through today, we're going to look at and be converting. We're going to say 103.2 joules. We're going to convert that into kilojoules. Now, hopefully you can see right here already we've got kind of a proportion set up. So if I erase these here, I can write in my proportion. And now we can just cross multiply. So I'm going to do 1,000 times 1, which is 1,000. And then 1 times 103.2. Oh, down here is an x, so that needs to be 1,000x. And then I would just divide this by 1,000. And that would give me 0.1032 kilojoules. So that's one way to do this. Now let's use the same numbers, and I'll show you a different way, maybe a simpler way, kind of a shortcut way to do this. So we're still going to use the 103.2 joules, and we want to convert that into kilojoules. Remember, 1,000 joules equals 1 kilojoule. So now this time when I go through, remember there's 1,000 joules into 1 kilojoule. So to convert 103.2 joules to kilojoules, all I'm going to do is divide by 1,000 and just move the decimal point 3 times to the left. 1, 2, 3. So my answer is going to be 0.1032 kilojoules. So kind of a shortcut way, if you can remember, that to go from joules to kilojoules, you're going to divide by 1,000. And we get the same answer that we got before. All right, now we're going to go ahead and practice the conversion from kilojoules to joules. We're going to do the opposite process, kilojoules to joules. All right, in this example, we're going to convert kilojoules to joules. So let's say I have 32.4 kilojoules, and I want to convert that into joules. Okay, now the example that we just went through, converting from joules to kilojoules, we did a proportion. We could set that up, and we could do that again. We could say that 1 kilojoule equals 1,000 joules, and now we have our proportion, and we just cross multiply and divide. Or we can remember our shortcut, and if going from joules to kilojoules, we moved the decimal point 3 times to the left, then going from kilojoules to joules, we're going to move the decimal 3 times to the right. So I'm going to take this and move it 3 times. 1, 2, 3. These empty spaces I'm going to fill in with zeros. So I'm going to have 32,400 joules is going to be my answer. Now, if I had done the cross multiplication and divide with my proportion, I would get the same answer. If you want to, you can go ahead and check that, but you're going to get the same answer whether you do it the long way with the proportions or whether you do it the shortcut just by moving the decimal point. You're going to get the same answer. And just as a review, let's do one practice of changing Celsius temperatures to Kelvin. We'll do an example of that. All right, so let's review how to convert from degrees Celsius to Kelvin. Remember that 0 degrees Celsius is equal to 273 Kelvin. Now, if you look it up online, it'll say 273.15, but that 0.15 isn't going to mean that big of a difference for what we're doing in our class, so we're just going to round it to 273. So let's say I have 25 degrees Celsius. Well, I'm just going to add 273 to that, and that would give me 298 Kelvin. And so that would be our answer there. Remember, when we go from Celsius to Kelvin, we're going to add 273. And now let's practice the reverse process where we'll go from Kelvin to degrees Celsius. All right, now to review going from Kelvin to degrees Celsius, remember that 0K is equal to negative 273 degrees Celsius. Remember, if you look this up online, it'll say 273.15, but we're going to ignore that 0.15 degrees in the calculations that we're doing because it's not going to make that big of a difference. It's not going to make a difference. It's not going to make a big enough difference that we care about it. So if I'm converting from Kelvin to Celsius, let's say I have 300 degrees Celsius and I want to convert that into degrees Celsius, I'm just going to subtract 273, and that's going to give me 27 degrees Celsius. And so that's how we would do that. Remember, when we go from Kelvin to Celsius, we subtract 273. All right, now since we're looking at heat, and heat is the transfer of energy from one object to the next, an object of higher temperature to an object of lower temperature, what we're really doing is we're comparing the energy in the products to the energy in the reactants. Do the products have more energy or do they have less energy? Well, if they have less energy, then that reaction is exothermic. Because the products have less, they must have released, some of that energy must have been released into the environment. If the products have more energy, then that's what we're going to classify an endothermic reaction. Because the products have more energy, they must have absorbed that energy from the environment, making it endothermic. If you want to set up a math equation, we're going to say the energy of the products minus the energy of the reactants is going to be our change in energy. And again, if the energy of products is more than the energy of reactants, that's going to be endothermic. If the energy of the products is less than the energy of the reactants, that's going to be exothermic. When we're talking about change, there's some notation, some symbols that we use to help simplify things as we're writing this all out. Because writing change in energy or energy, it's going to take a long time. So we have symbols to help us with that. We're going to use this symbol here. This is the Greek letter delta. It looks like a triangle. This is the Greek letter delta, the capital delta. And it means change in. So whenever you see a triangle like that, before a variable, before something, we're talking about a change in. So for example, if I have delta T, T standing for temperature, I'm talking about the change in temperature. Now when I say it out loud, I'm going to say delta T. It's also acceptable to say change in T, but delta T is going to be way more common as you move forward in your science education. If I have a delta and then a capital E, E standing for energy, again, I can say this delta E, or I can say change in E or change in energy. It's the same thing. You ever see that little triangle, that delta symbol? We're talking about the change. And again, how do I... All right, so then using those symbols for measuring energy transfer, again, I'm comparing the energy in the products to the energy in the reactants. So if my delta E or my delta T is less than 0, that means my products, remember I always do products minus reactants. Always do products minus reactants. If products minus reactants is less than 0, that means my products have less energy than my reactants. Well, what happened to that energy? Well, it was released into the environment. It was exothermic. If my delta E is greater than 0, meaning my products have more energy than what they started, that's going to be endothermic, because during the process, energy was absorbed into my system. So let's play a game. It's called exothermic or endothermic. I wish I had some epic theme music to play during the game, but we're on a budget here, so we'll just have to bear with me. All right, so let's start with this one. My delta E, my change in energy, is negative 57 joules. Now what this means is that my products have 57 joules less than my reactants. Now is that going to be exothermic or is that going to be endothermic? Well, of course, that's going to be exothermic. My products have 57 joules less than my products. Well, where did that energy go? It was released into the environment. It was exothermic. Here's another example. My delta E is 657 kilojoules, 657,000 joules. Is this exothermic or is this endothermic? Well, of course, this is endothermic. My products have more energy than my reactants, which is why delta E is positive. Well, where did that energy come from? Well, of course, it was absorbed from the environment. Here's another example. My delta T is 30 degrees. My products have a higher temperature than my reactants. Well, what happened? Where did that extra kinetic energy come from? Well, it must have come from the environment. That is an endothermic reaction. Energy was absorbed from the outside, which is why my temperature of my products is greater than the temperature of my reactants. Last example, my delta T is negative 7 degrees Celsius. Is this exothermic or is this endothermic? Well, as you probably guessed, this is exothermic. My products are 7 degrees cooler, have 7 degrees lower temperature than my reactants. My products have less kinetic energy than my reactants. Well, where did that energy go? Well, it was released into the environment. So here's just a couple of examples where we can use the change in energy or the change in temperature to figure out, is this exothermic or is this endothermic, this process that's happening. Now again, we're talking about chemical reactions, chemical equations. If you have questions about physical changes, changing states of matter, there's a video posted on my channel. Go back and watch that when we first talked about states of matter and going from solid to liquid and liquid to gas. And it talks about which of those processes are endothermic and which are exothermic. If you have any questions on anything that was discussed in this video, feel free to drop a comment or get in contact with me, send me an email, and we can clear up any of those problems. There is a Quizlet set that is attached to this video. I'll post the link in the description that goes over all of the vocab that's covered in this video. So if you have any questions, feel free to let me know. Otherwise, make sure to hit that like and subscribe button, and I'll see you guys next time. Have a good one.